Okay, so let's begin. So it might be the case that today's lecture might also be slightly on the shorter side because there's only uh, one thing I want to do in the agenda, which is the quadratic sieve, and depending on towards the end, we will see if I can sort of slowly at least segue into the number field sieve, which is going to be the topic of the next lecture. But just a high level, some preliminaries for it. Okay, so there's going to be a long recap because we're going to go over what we had done in Dixon's algorithm, etc. Because all of the quadratic sieve and various other optimizations we did last time, they're all optimizations on top of the standard template of using the congruence of squares method. So let's just go over this again. So the congruence of squares method, the goal is to basically try and find two elements, x and y, mod n, that such that their squares are the same. So the squares are equal mod n, and this must be a non-trivial pair x comma y in the sense that x is neither plus y or minus y. Okay, and we saw based on Chinese remainder theorem is that if n has multiple prime factors, then there are actually lots of such x's and y's that will have this property, and therefore the goal is to try and find one such pair. And in almost all of these methods that involve looking for smooth numbers, where you want to say that I want to pick a number and hope that the number of prime factors, all its prime factors are not larger than a certain threshold or something. Whenever you're dealing with situations of that sort, somehow these functions become very, very important. Okay, I think the first person to sort of start using these sort of L function was Brill or something. I might be butchering the name, but the idea that this L function is very useful for doing these estimates because all of them will eventually come down to what is the right choice of B. You will have a smoothness threshold, you have a general template involving this threshold, and you are trying to figure out what should I choose B as. And once you get familiar with this particular the L notation, things become very easy to analyze exactly what is going on, etc. And the key point is because of the following fact, which is that if your smoothness threshold can be expressed as this L parameter, I'm dropping the subscript n because throughout this n will be fixed. Everything is in terms of this one, this n. So if you're interested in, okay, this is my range, I'm interested in the first m numbers, and I want to know how many of them are B smooth. And suppose I have a way of expressing both m and b in terms of these L parameters, and normally all of this R, R, S, beta, alpha, they're usually constants. They're constants that are independent of the number n. Okay, so therefore, in some sense, for a fact that, L half is certainly bigger than L 1/3 and so on, because the exponent of log n is going to be larger. It doesn't quite matter whether this constant is a little larger or not, as long as they are constants. The S is already giving you an order in terms of how much they grow, etc. Okay, so what does this lemma say? It says something about the density of B smooth numbers in the range 1 through n. And it roughly says that the probability of, when you pick a random number and you ask, what is the probability that it is B smooth? That probability is this. So it's basically R minus S and alpha by beta times R minus S. There is a minus because this has to be less than 1, of course. Okay, so it's like saying that among the first m numbers, this many of them are B smooth. And often the heuristic that will often happen is that we will have some set of m numbers, not particularly in this range 1 through m or something, but it will be some set of m numbers that are no larger than something. And we will just assume that the density is roughly this. So those are heuristics that will end up coming in terms of the probability of a number being smooth in this range that we are looking at. Okay, so another way to think of this.
Sorry, you said, the minus sign. Is this the fraction of B?
Yeah, this is that. So it's just saying the number of things is going to be m times this fraction.
Right.
Okay. But on the other hand, if you want to think of it in terms of, suppose I want to keep picking up random numbers from 1 through m until I get a B smooth number, how many samples do I need? So the expected sample complexity will be the inverse of this, which is going to be this quantity. So if you're looking for smooth numbers, you will need to try this many times until you get one smooth number. And then you might have to keep doing this again and again and again. Okay, so this was the basics in terms of why L functions are useful, just because of the fact that this expected thing also happens to be something in terms of this L. So dealing with the best choice of B, etc., turns out to be far easier. Okay, so what is the Morrison-Brill-Hart approach? So the Morrison-Brill-Hart approach has a bunch, roughly, I don't know, 3 steps that I think of. The first one is finding all the primes. So you set yourself some smoothness parameter B. Okay, we'll have to figure out what is the right way to optimize this, but you set some smoothness parameter B. And first thing you do is you find all the primes within 1 through B. And at this point, I mean, like you don't mind spending order B time or O tilde of B time, just because the other things are going to actually be more costly. So this is something that is usually, I mean, you can just go over each of them and figure out which of them are primes and which of them are not primes. Maybe run the AKS test, run the Miller-Rebel test, whatever. Okay, and let's assume that the number of primes in the 1 through B is about R of them. And R is like roughly B over log B. So if you're ignoring log factors, this is like roughly B. You're just ignoring any such things. Next comes the data collection step, which is you're going to choose some AIs according to some, I mean, different algorithms choose different choices of AIs. Okay, but the goal you're looking for is looking for things of the form AI squared equals yi mod n, such that this yi happens to be B smooth. And the way this is done is you will pick your AIs according to whatever pattern that you want based on the algorithm and hope that this yi is B smooth. And again, as you would expect, I mean, the smaller the B is, the chance that the yi is B smooth is going to be far smaller, which means that you will have to try a lot more samples. But on the other hand, if B is too large, then all the other running times, etc., will start taking a hit. So there is some Goldilocks range for choosing what B should be. Okay, so this is the thing. Data collection is just going to be try and find various congruences where AI squared mod n happens to be B smooth. Okay, so that is the data collection step. Next is the congruence of square step. Now, because all of these yi's are B smooth, you can also find the factorization of them. Okay, and now we just write this down as a big matrix where the rows are, the exponent vectors are added as rows. And what are we asking? We are asking, is there a product of these yi's that gives me a square? Which is the same thing as saying, is there a suitable sum of, can I find a subset of rows, a non-zero subset of rows, such that when I add up those exponent vectors, every exponent vector now becomes an even number. Okay, and this is just, you are doing linear algebra over F2. So you're writing down something like a I don't know, B cross B matrix roughly, and saying that, okay, can I choose a row combination such that I get 0 mod 2? And you do that. Once you do that, you get a product of these yi's that happens to have all of these exponent vectors being even, which means that this yi is a square. So now that gives you your congruence of square. You just set your alpha. Oh, I had used x earlier, but doesn't matter. I mean, you choose alpha to be equal to the product of these AIs, beta to be equal to the product of the BIs, and by construction, because alpha I squared was equal to yi mod n, you know that alpha squared is equal to beta squared. Okay, and therefore now you just hope that M has a non-trivial GCD with one of these two things, alpha plus beta or alpha minus beta, and which, if you get a non-trivial thing, you return. Okay, otherwise you'll try it again, but typically this happens with probability 1/4 or something like that. I mean, it'll happen with probability at least 1/4 if you find alphas and betas that are this thing. So therefore, I mean, this is usually not much of a cost. It's the rest of the operations that are expensive. So this is the overall template, but it's just that different algorithms do slightly different things. So for example, the Brill-Hart and Morrison approach. So each of these AI squareds, I mean, the AI that, or rather, so AI was basically equal to, sorry, how do I put this? Maybe I should write it as this. So yi was equal to, you look at square root n, take the ceiling of this, plus I the whole squared minus n. Okay, those were the y's that you started off with. So in some sense, the ai is equal to square root n plus I, and the yi is equal to, basically you just go mod n, and as long as I is small, mod n will mean you subtract one copy of n. Okay, and in fact, the Brill-Morrison thing, they did something on top of this. They used something called continued fractions. Okay, but we don't need to get into it. But this gave us some heuristic improvements and stuff like that. Dixon's approach, on the other hand, was like very, very simple, which is to just say, let's just pick each AI at random from CN. I mean, why are we trying to be clever about choosing these AIs at all? Let's just be random about this. And I mean, even though it's a little slower than what you get through this the Brill-Morrison sort of approach, the whole point is that this gives you a rigorous analysis. I mean, you can provably show that the expected running time of this algorithm is L half or something. Okay, so these were the things, but of course you can imagine there could be different schemes of choosing what these AIs are, but these are the two schemes that we'll be looking at. Okay, so let's do a little bit of the time complexity analysis. So the time complexity analysis of this of Dixon's algorithm is roughly split into three parts. So this is the finding prime step. And we are not being clever here at all. We are just basically saying that let's run through the first B numbers, run the AKS test or something on all of them. But since anyway things are randomized, you could basically say, okay, let's run the Miller-Rabin test on all of them, whatever. So we do something like that. Okay, and this is the data collection step. Okay, and let's just see what each of them are. So this is the number of congruences we need. And we needed r plus 1 of them, where r is the number of primes in the range 1 through b. Okay, because we are trying to find a suitable linear combination. So this is number of samples per congruence. Okay, because we are basically in Dixon's algorithm, we are basically saying each of these yi, the ai squared mod n, it will look like a random number in 1 through n. So you're basically asking what is the probability that the residue, whatever is this random number in 1 through n, what's the probability that it is a B smooth number? And that happens to be the inverse of this thing. And therefore, so this is what you end up with. And this is the time to test smoothness. Because for each of these things, I need to first run some smoothness test. Like see if if there are any prime factors that it has that's larger than p. And the naive way of doing it is basically let's go through all the primes and just see which of them divide and note. So that is the data collection step, and then there is the building the congruence step. Building the congruence. So this is just linear algebra of something like a B cross B matrix. Like you're trying to find a kernel in it or something of that sort. Okay, so this was the rough thing. So, and if you put them all together, what you end up getting is you'll end up with something of this form. So the best thing that you can do is like if your S is too small, that is if your choice of B was such that S was less than half, okay, then this number becomes more than half. This is like bigger than L half. So that will start dominating. But on the other hand, if S was more than half, then all of these other terms will start dominating. So the best thing to do is somehow balance the two and you choose S equal to half. And if you just stare at this and so on, what you end up with is this. Because this is a beta, and this looks like 1 by 2 beta. So that's why you get a 2 beta plus 1 by 2 beta. And the B cube becomes a 3 beta. So that's what we have here. And this we saw that is optimized at beta equal to half, and therefore you have a rigorous running time analysis of L half comma 2. Okay. And then what did we do? We basically threw a bunch of optimizations of trying to reduce these constants. So the first optimization was the fact that, okay, I want to do a linear algebra on a B cross B matrix, but it's not some arbitrary B cross B matrix. In fact, every row has very few non-zero entries. And we said that, oh, therefore you are looking at a sparse matrix and trying to find some kernel within a sparse matrix or something. And turns out there are methods to do that in linear time. Okay, so instead of spending order B cube time, you can actually end up spending just order B squared time. Okay, there's some logs involved, which will again be very good. Okay, now what this does is it replaces this 3 beta by a 2 beta. Okay, but unfortunately at this point we still haven't, it doesn't help, because I mean the optimum is still at beta equal to half and you still end up with L half comma. So it doesn't help yet. And then comes the next trick, which is, why are we choosing these YIs at random? And let's choose these YIs in the Brill Morrison sort of approach. Okay. And what's the point of doing this? The point of doing this is that when you choose for small i's, sorry, this is not AI, this should be YI. Each of these YIs, notice that is about order root n. Okay. And eventually, the sort of i's that we will be dealing with is only as long until we get something like B, we have something like R plus 1 many B smooth YIs. So the number of i's that I need to go is nowhere close to root n. So it's like far, far smaller. So therefore, all of these numbers are actually going to be small. Okay. So then the probability of, so the point is heuristically what we want to say is the following. Each of these YIs are some number which is of size at most order root n. And I want to know, in order to get one B smooth number, how many tries do I need? So previously, the density estimate we used was, you are saying among the first n numbers, how many of them were B smooth, or what fraction of them were B smooth. Now I know for a fact that these YIs are only bounded in the range of about order root n. It's not as large as n at all. So then the hope is, okay, so then heuristically, maybe the fraction of these YIs that happen to be B smooth is roughly what fraction of the first about order root n numbers happen to be B smooth. Okay, and because root n, this is equal to L of 1 comma half as opposed to L of 1 comma 1, which is what n was. This 1 by 2 beta ends up becoming something like 1 by 4 beta. Because if you recall, this is roughly, where was that bound? It was something like this term. Previously, alpha was equal to 1, beta was whatever beta was, R was 1. So you got 1 minus S by 2. But now alpha itself is half. So you get 1 minus S by 4 as opposed to 1 minus S by 2. Whatever. So therefore you end up getting 1 by 2 beta. Oh, sorry, not here. 1 by 4 beta as opposed to 1 by 2 beta. Okay. And now you can apply your optimization, etc. And now the optimization actually happens at beta being 1 by 2 root 2 or something. And you get L half comma root 2, which is better than L half comma 2. Okay. So this is what we did last time. So today's lecture is going to build on top of this particular choice of YIs. And we are going to see something called the quadratic sieve that is due to Carl Pomerance, which achieves the bound that you will end up getting is like you shave this 2 beta into a beta. That's the gain that you do. And as a result, you end up, this gets optimized at beta equal to half, and you end up with L half comma 1.
What I thought there was something you said gives us L 1/3 comma 1.
Yeah, so that's what is called the number field sieve.
But that's the next.
That's the next thing. But in fact, the number field sieve doesn't need the quadratic sieve, but we'll see. I mean, like it's again, towards the end of the lecture, I'll tell you. I mean, I'll try and lead towards it, and the next lecture we will see in a bit more detail, but nowhere close to a full description of the NFS. Okay, so this is called the quadratic sieve, and this is what we are going to do. Okay, and the way we are going to do this is try and revisit the steps that we haven't tried to optimize yet. Okay, there are two steps that we haven't tried to optimize yet. One was finding the primes in 1 through b. That was a step we basically said that, okay, it takes O tilde b time and let's just do that. And second was we needed to run some smoothness test on a whole bunch of numbers. And we basically said that each smoothness test takes a certain amount of time. And I have this many numbers. So it is this times the time taken per smoothness test. And we want to know if these are things that we can optimize. And the two are going to be related. So I'm going to start off with this thing of, suppose you wanted to find, all primes in the range 1 through n. Okay, let's just go back to that and ask ourselves how much time will this take. Okay, so the stupid algorithm, which is called trial division. Okay, for each I, run AKS. Okay, so if you look at the time taken here, this is basically going to be O of n times, I don't know, log n to the 6 or something like that. I mean, whatever is the time taken for AKS. Okay, so this is what we are going to do. But the whole point of, why is this not the best algorithm you could do? Like, suppose you found out that, so 3 is a prime. But this particular approach is sort of, okay, let's say that I don't just want to find all primes in this, and I also want to factorize the rest. Okay, then it almost seems like I need to run an n squared time, because I first need to find all the primes. And then for each number that is there, I need to divide by each of the primes and figure out what the factorization, etc. is. So, and something like O tilde of n squared, if we also want to factorize. Okay, just because we're going to try out all possible primes in the range 1 through n, try it out against every possible pair. But this is obviously seems like a very wasteful way of doing things. Okay, so there is a better way, and this is something that I'm sure you have seen earlier, which is called the sieve of Eratosthenes. Okay, so let's just do it by an example. Okay, and because I know we have seen this, I'm just going to do it. In full, in its entirety, just because we can appreciate certain things that we take for granted, because these are what we're going to exploit in the quadratic sieve. So, okay, so welcome back. I'm sorry about this delay. So, okay, so we did this thing, we divided by 2 all of these numbers, and then we mark 3, and then we scratch out all multiples of 3. I'm actually scratching the multiples of 3 that were already scratched also, and this is for a specific reason, the point I want to make towards the end. Okay, so 39, 42, 45, 48. Okay, then we take 5 and we scratch out all multiples of 5. Okay, then we take 7, scratch out all multiples of 7, 21, 35, 42, and that's it. And at this point, we can basically safely say that because we've gone up till square root of the range 50 or something, because I know that the next number is already square is larger than that. Basically, all the numbers that have not been scratched out, they are the primes. Okay, so we have just found. Oh, sorry, I forgot to scratch this out. Okay, so these are the primes that we have found. So I want to point out something. So notice that if you just think of it the following way, what did we do? We started off with 2, went to every even number and scratched those out. And then we went to 3, and then went to every multiple of 3, scratched those out. And this is what we kept doing. And I want to point out, we never even visited the number 43. But we know for a fact that 43 is a prime. So similarly, we never visited, I mean, all the numbers that were bigger than 7, all the primes that are bigger than 7, we never had to visit that cell. Okay. So previously when we were doing this sort of, trial division way of computing factorization. So notice that, by the way, it's very easy to modify the algorithm such that all the numbers that you scratched out, you actually get their prime factors also. Because why did I scratch this 2 out? Because I knew for a fact it was divisible by 2. But I could have divided it by 2. Instead of scratching it out, I'll replace 4 by a 2. Okay, and I'll divide by 2. I'll divide by as many powers of 2 as possible, and so on. I could have done all of this. So the whole point is you manage to factorize these numbers, and some of them you never even visited them. So that's what that was what was sort of one of the better things that we could do in the Sieve here. But I want to focus on one thing which we sort of take for granted, but I just want to spend some time on this. So for example, we went over 3 and we wanted to say what are the numbers that are divisible by 3, and we basically moved 3 steps. We got rid of this, got rid of this, etc., etc. I mean, notice that for a fact that for every prime p, you never even had any doubt that this number could potentially be divisible by 3 or something. There was no confusion there. I mean, just because of the fact that 6 is divisible by 3, you knew for a fact you never had to divide 8 by 3. Because it won't divide. So why would I waste time trying to do that? So you only ended up dividing things by 3 that you knew were divisible by 3 to begin with. Okay, so it's a simple observation, but it's an important one because we are going to make use of it in the quadratic sieve, which is the only yi's. Okay, here yi is equal to I. Okay, the only yi's that could possibly have been divisible by p are those whose index was a multiple of p. Okay, and therefore, when you're dividing a number by 2 or by 3 or by 7 or something, the only numbers that you will even attempt to do this are those indices that happen to be multiples of 2 or 3 or 7 respectively. Okay, it's a simple fact, but it's a very important thing, and this was the reason why we never divided something like 43 by anything. Okay, when we were doing this trial division calculation, we were doing something stupid by saying that for every number, I could potentially have divided these number by all the primes in the range that I want to, and therefore I ended up with a quadratic thing. But the sieve basically tells you that no, that's a really stupid thing to do. Why would you ever want to divide 43 by anything? There's no reason for you to divide 43 by anything. Okay, so now let's ask ourselves, how many numbers did we actually end up visiting? Like the above, when we ran this algorithm, there was a bunch of scratches that we kept doing. Okay, how many scratches did I do? Because roughly each scratch corresponds to one division. Okay, so you're going to do something for every such scratch, and I want to know how many such scratches did I have.
Like if we are looking at n, then it's like I think we looked at like n by 2 plus n by 3 plus.
Right. So n by 2 plus n by 3 plus what's the next one?
Like the next all the primes, right?
Right. N by 5 plus blah blah blah. So until n by the largest whatever p something, whatever was the largest prime. So we're basically saying I want to know how large is this sum, n by p, where p less than or equal to n and prime. Okay, now I'll just state it, I won't prove it here. Turns out this is roughly n log n. So the inverse of reciprocals of primes until a bound n turns out to be like log n. Okay, the proof is not hard. In fact, Wikipedia does have a proof. I think I've forgotten exactly what this theorem is called, but I'll add a reference to this on the thing or something. So which means that the previous algorithm where we basically said if you want to factorize all of them, or let's say you just want to find all the primes, it was n log n power 6. Okay, but now we are basically saying that you can actually do this in n log n many divisions in some sense. Okay, but in the grand scheme of things, it's not really much of a saving. Okay, so now let's try to modify and ask a slightly different question. Now I give you the range 1 through n, and I ask you to find all these smooth numbers. Okay, how would we do this? Okay, and not just B smooth numbers. I want to find, and let's say, and factorize.
It's sort of the same thing, right? Except like you just go till like the number left is like B. Like you are having.
That's right. So, but let's just to compare, we were doing. Suppose we did trial division. What would we have done? We would basically have said there are n numbers that I have. Okay, and I have potentially about B primes, like roughly B primes. So I'm just going to divide every number by every prime to find out what is the largest power of it that divides. Okay, so the naive trial division approach is going to be n times p. Okay, this is like divide every number by every prime. Okay, and do this. But you can use the sieve instead, which is just the following. So you initialize your array or whatever, where here yi is equal to I. Okay, which is just 1 through n written down. Okay, and now for all the primes that you have, let's do the following. What are the numbers I should even try dividing by a prime p? The only indices I should even attempt to divide by p is those I that happen to be 0 mod p. Because I know for a fact that it's only those yi's that are going to be divisible by p. And for each such yi, let's divide by p as many times as we can. Okay, so you have found out the largest power of p that divides the yi, so that yi has become smaller. So in the previous C, what would have happened is when I did it by 2, I would have replaced this with 1. I would have replaced this with 2 squared. I would have replaced this with 2 into 3. And at this point, I don't know if 3 can be factorized more. Okay, and this is going to be 2 power 3, and this is going to be 2 into 5, etc., etc. You see what's happening. And in the next step, we'll divide by 3. And you'll keep doing this. Notice that what is going to happen to the primes are all going to end up becoming 1. In this process. So, so here what we want to say is that if you're only going to run over all those primes that are less than or equal to b, the only indices that would have become 1 right now is if these primes were the only prime factors that those numbers had. So that's going to tell you exactly which of the numbers are b smooth. And if you keep track of the factorization, you also get the factorization in the process. Okay, so good. So now let's ask ourselves, how many divisions did we end up doing? Okay, so how many times did we divide by 2? So there were n by 2 times like earlier, but some of these numbers I might have to divide by 2 once more because a larger power of 2 divides it. Like for example, 4 or 8 or 12 or whatever. Okay, which means I might have to divide twice for all those numbers that were actually divisible by 2 squared. Okay, plus n by 2 cube, etc., etc. And then the same thing for n by 3, plus n by 3 squared, blah, 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 and so on. So for each prime, it's similar to the previous sum, but now there are these summation n over pi per whatever. Okay, so what does this eventually come down to? It comes down to you sum over all primes less than or equal to b. Okay, this is a prime. Okay, and you sum over all a greater than or equal to 1, say, until whatever it can be. And this is going to be n by p power n. Okay, so what is this equal to? Let me just write the a equal to 1 term separately because that we have calculated. So n by p, where p is less than or equal to b prime. Okay, and let's do the following, plus again p less than or equal to b prime. Okay, so this is going to be n by p power a, where a is at least 2. And now, I mean, I'm going to put a less than or equal to and make this go all the way till infinity, because I can apply one of these geometric sums or whatever. Okay, the first term, I already know this is like n log b, because the sum of the reciprocals of all primes until b is log b. Okay, it's called Merton's second theorem. Yeah, okay, now I remember what it was. Okay, but let's do the other thing. What is that going to be? This is the sum over all primes, whatever, p less than or equal to b or something. And what is this going to be? This is going to be, so there is a factor of n, let me just pull that out. So it's 1 over p squared plus 1 over p cubed, blah, 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 blah. So it's going to be 1 over p squared by 1 minus 1 over p. Okay, since all primes are at least 2, this quantity, in fact, I can, since I'm putting in, so this can be written as, this is at most order of n log b plus 2n into summation 1 over p squared. Okay, just because of the fact that this number, whatever it is, it has to be at least a half. Okay, because all primes are at least 2. So you get 2n into 1 over p squared. And I guess you know that this actually converges to some constant. Even if I not just range over all primes, if I range over all possible numbers, it converges to something like pi squared by 6. Okay, so this is a constant. So which basically tells us that this entire thing is like order n log b. Okay, so just to get a sense of what has happened, I wanted to factorize, I wanted to find out all the numbers in 1 through n that happen to be b smooth. Okay, and whatever was b smooth, I want to factorize all of them. The naive approach was taking n times b, which means roughly per element, I was spending b amount of time, more or less. But now the time complexity is something like O of n log b, which means it's like roughly unit time per element. Okay, and if we can somehow make use of this in our factorization algorithm, we might be able to knock off one factor of b that was there in this smoothness test. Because we basically wanted to say, I have this many things. I wanted to find out all the smooth numbers and factorize the smooth numbers that I have found. Okay, and we were saying that, okay, each such test takes about order b time. And now we want to say, no, that is like way too much. Why do you want to spend that much time? We want to do something better. Okay, good. So now how do we use this in our algorithm? The thing is, previously in what we were doing, yi was equal to I. Okay, so therefore you knew exactly which of these yi should you even try to divide by p. Okay, but now this yi is going to be some ugly set of sequences. I mean, it's some ugly sequence that you're going to end up getting. But I still want to ask, okay, so can we still see this sequence? Is the sequence structured enough that we can still attempt to do what we did in the sieve of Eratosthenes? Okay, so the key question here is the following. So for a fixed prime, okay, which of these yi's are divisible by p? Like, what are the yi's that you should even attempt to divide by p? Okay, any thoughts? How do you know which yi's to try?
So, where I is divisible by p.
It's not clear, right? Because it's like it's something plus I the whole squared minus some other thing.
Yeah, so this, I mean okay.
By the way, this prime p need not divide n or anything. I mean, right? This is some fixed prime. Like for example, I want to know what are the yi's that are divisible by 2. And it's unclear at the moment. It seems like, doesn't seem, I don't exactly know what to do here.
No, because I was trying to think maybe like okay, not accurate, but the n like the root n square is cancelled off by the n, and you have something like I square plus 2i root n. So certainly, if you want some yi to be divisible by p, the i's should be divisible by p, right?
Actually, that is true. So let's just do the following. So you are basically saying that this looks, this yi is basically equal to, no, but there is it. This root n is not quite n. There is some other thing.
Yeah.
But it actually looks like m plus I the whole square minus n. And I want to know, what can I say about I if I want this to be equal to 0 mod p? Okay. So this implies that I mod p must be a root of m plus x the whole squared minus n over fp. Right? Like whatever is the residue of I mod p, it must be such that this number suddenly now becomes 0 mod p. How many different roots can it have? Okay. So there are like at most 2 roots. And can we find those 2 roots? All I give you is this particular equation.
You can go over all the p's.
Actually, this time you can actually go over all the p's, but in fact, there's a better way of doing it. You know how to factorize over fp.
Oh, okay.
So all you're saying is that this is a quadratic polynomial. Let's just factorize this polynomial over fp. If there are roots, it will split as x minus alpha times x minus beta. So you know what alphas and betas are. Great. So for a prime, there are 2 roots. Okay. So this implies that either this I is congruent to some alpha p mod p, or I is congruent to beta p mod p, where alpha p and beta p happens to be those 2. So where alpha p and beta p are the roots of m plus x the whole squared minus capital N over fp. So as you said, you can either go over all the things. It doesn't hurt you to do this, but since we are trying to be as efficient as possible, you might as well factorize it and find that. This is just taking GCD with x bar p minus x and see if you get what you get. Okay, great. So this is the quadratic sieve. Okay. Again, you're going to run over all possible P1 through PR. Okay. So the sieve consists of yi equal to this guy. Sorry, yi looks like m plus I the whole squared minus n. Okay, and I want to know which of these i's should I even try to divide by p. Okay, and the way we are going to do this is first we'll compute the 2 roots for m plus x over fp. For every fixed prime, we'll compute these 2 roots. And now sieve over all possible whatever, alpha p mod p things. Again, you keep shifting by like p steps and keep dividing by p as long as you can. Then you do the same thing by starting from beta p and then shifting by p steps until you cut. Okay, and all the things that used to be b smooth would now have gotten completely factored. And you know for a fact that things that didn't get completely factored are not b smooth. So you don't need to worry about them. Just throw those in. Okay, and that's it. So what is the total time taken? Okay, so the total time taken is, it's a question of what is the range that you need to work with. So this is going to be O tilde of m log b like last time, where this m basically equal to r plus 1 into number of samples per smoothness. Because I eventually needed R+1 smooth yi's. So for that, maybe I needed to try y1, y2 all the way till y r+1 times something. Whatever was you take into account the density part of it. Okay. So that is my M. And now we are saying among these M yi's that you have built this way, which of them are B smooth and can you compute their factorization? And we are basically saying, yes, I can do all of that in just M log B time. So this thing earlier we were spending M into B has now suddenly become M into log. Okay. So what happens to the overall running time? So the overall running time, there is still going to be this initial part of getting B. I mean, this is the finding primes business. Okay. Plus, now let's try to do this data collection step together in some sense. So basically what is going to happen, there's going to be order B times the number of things per sample. Okay. In fact, what I'm writing here is like this must have actually been order M times log B. That's what this is supposed to be. Plus, again, there is a linear algebra part, which we have said that this is like something quoted. Okay, and what is M going to be? So this is going, let's put them all together. So again, my B is going to be L of half comma beta. Okay, so what is this going to be? So this is going to be L of half comma beta plus L of half comma beta plus 1 over 4 beta. Earlier, I used to multiply this with L of half comma beta. But now that has now become a log B sort of factor, which I can now ignore. So, okay, so maybe I'll split this. So what was M? The number of samples that we needed was L of half comma beta. Sorry, the number of congruences we needed was L of half comma beta. But in order to get one smooth congruence, I needed to try out many other congruences. How many congruences did I need to try out? That was another L of half comma 1 over 4 beta. And earlier, I used to multiply this with another factor of B because that was the time that it took for smoothness test. But overall, now we know that that has now been replaced by a log B, which is basically nothing. Okay, so you only have this plus L of half comma 2 beta. Okay, so overall, you're basically going to end up getting L of half comma, so sorry, this is the max of beta plus 1 by 4 beta and 2 beta. Okay, and this is L of half comma 1 when beta equal to half. Okay, and that is this is the quadratic sieve. Okay, so it's a pretty cool idea of sort of saying that you want to say that it's too much to say that I will be spending the amount of time per smoothness test. I mean, clearly, if a number, I mean, like if you know for a fact that this number is not going to be divisible by 2, why would you even attempt dividing this by? So, and even though your sequence looks like an ugly sequence, where it looks like, m plus I the whole squared minus n or something, at the end of the day, it's a quadratic polynomial. And at best, there may be 2 possible residue classes, where your number could be divisible by p. So let's just go through both of the residue classes and beta. Okay, and that completes the quadratic sieve. And this is it's actually not too difficult to implement if one really puts their mind to it or something. And for a long time, this was the king of sort of all factorization algorithms and the tremendous successes that were there. And so now I'm going to spend some time to at least try and tell you how you can hope to improve the quadratic sieve and say that especially if you wanted to breach L half, Okay, what can you possibly do? Okay, so I want to revisit something that happened a little earlier. Okay, so let's just ask ourselves, why does it seem like you can't breach L half, naively? Okay, so we had a particular smoothness threshold. Okay, now let's say the number of, therefore, once you have a certain smoothness threshold, the number of congruences you need in order to build your congruence of squares is roughly B. Again, I'm ignoring log factors. Okay, but suppose you set B to be equal to half minus delta comma beta. Again, I'm not insisting that delta is positive or negative. I mean, we'll try both and see what happens. But I'm just saying that delta and beta are both constants. Okay, so the number of, okay, so let me not do this. The number of tries until we get a smooth yi was basically, what is this going to be? So this is going to be L of half plus delta, comma 1 by beta into half plus delta. This is the number of tries you will end up needing. Okay, if all you know is that these yi's are less than or equal to capital N, then this is the best you can do. Okay, which basically means that, if delta, beta, they're all constants, this is some constant. So it's really going to be dominated by this versus this. So if I had chosen delta to be a positive number that is strictly greater than 0, then this will start dominating the running time. If I had chosen delta to be a negative number, then this will start dominating the running time. And this beta is not particularly helping me with respect to what I can do. Okay, and this was what Dixon's algorithm did. And Morrison and Brill had said, if I can make this yi range smaller by about root n, then I can add one extra factor of 2 here. Okay, so that basically, at least it didn't change the story here, but it seems to change the story with respect to what constants show up here. Okay, it's not really saying much, but here's what I'm going to do. I'm going to assume that, let's just say that we believe in some miracles that end up happening, okay, which are somehow going to let us say that the yi's that you are going to deal with, things that you want to check for smoothness, etc., turns out to start looking like something like n power 1 over d. Okay, and d is actually going to be non-constant. It's going to actually grow with n, which means this n power 1 over d is way smaller than root n or anything. Okay, and I just want to know, suppose we were in this world, and suppose you had a choice of choosing this d the way you want. I want to know what could you have gotten? Like, what could you have done with this whole process? Okay, let's just play along. So this is again going to be something like L of 1 comma 1 over d. Right, like root n was L of 1 comma half. This is going to be L of 1 comma 1 over d. Yeah, this d is not a constant, so one needs to be a little careful, but let's just play along with this. Okay, so again, I'm going to say that my smoothness bound looks like L of s comma beta. Okay, now what is the expected number of tries I need to do until I encounter a smooth yi? Okay, this is the number of trials per smooth yi that you need. Okay, so if you calculate exactly what this is going to be, so this is going to be L of 1 minus s, and what is this going to be? 1 over d beta into 1 minus s. Okay, so how much time would it take? Let's forget all the other junk that we had. Let's just focus on computing the sort of congruences we want, the data collection step. Because you will end up needing B many congruences. And for every such congruence, you will need to spend this much time in order to get that congruence. Okay, so let's just write down what that expression is. I'm going to write it in terms of the exponential so that we get the sense of things. So this is going to be exponential in beta times log n to the s log n to the 1 minus s. Okay, that's just the B part. That's the number of congruences we need. But now for every such congruence, I have this nonsense. Okay, this into exponential in, let me write it as 1 minus s by beta, because this is a constant. And then there is a 1 by d. Okay, and now it's going to be log n per s, sorry, log n per 1 minus s and log n per s. So far, so good. Okay, so, okay, and now let's hypothetically assume that you had the ability to choose the d the way you want. Okay, turns out if d is equal to the following quantity, log n by log n are 1/3. It's like roughly cube root log n or something. Now let's see what would happen in the above expression. The first term is of course exactly the same. So it's going to be exponential in beta log n per s log n per 1 minus s times. So what is this going to be? So this is like a log n per 1 minus s plus 1 by d has another factor of log n to the 1/3. Okay, so this is going to be whatever, this is 1 minus s by beta or something. So this is going to be log n per 1 minus s minus 1/3. Okay, times log n per s plus 1/3. Okay, and now if you were told you have to optimize and choose the favorite s that you want, what would you end up choosing? You will choose it in such a way that this s matches this, right? So this turns out to be optimized as s equal to 1/3, and what you end up with is something like L 1/3 and something like beta plus 1 minus s by beta or something. Okay, I mean it's just it's a very vague thing. It's all fantasy at this point. So all we are trying to say is like if you have some way by which, just like between the Dixon's algorithm and the Brill-Morrison approach, the only difference we made was in Dixon's algorithm, these yi's, the best bound I could give for them was saying this yi is somewhere between 1 and n. And in the Brill-Morrison sort of approach, we basically said, no. If we are careful about the choice of these AIs and so on, you can make sure that this yi is at most rooted. And now we are saying, if by some miracle, you could somehow say that all the yi's you will deal with, things that you are hoping to be smooth. Okay, suppose they were only n power 1 over d, where d is this whatever, something like cube root of log n or something, then it suddenly feels like, oh, then I can probably get something like L1. Okay, by setting up the parameters appropriately. Okay, and turns out that the number field sieve is basically a way to make this fantasy real. Okay, so this is the goal of the number field sieve. The number field sieve is again going to try and find a congruence of squares. Okay, and it's going to do it in such a way that the only numbers you will deal with that you're hoping for smoothness happens to be something like n power 1 over d. And this d is something in your control. You can choose this d to be whatever you want. Normally, the sort of practical numbers, or rather, the sort of numbers for which it's even feasible to factor, this d turns out to be fairly small. It's like 3 or 5 or 7 or something like that. I mean, so like for example, if your number is something like 500 or like 100, I don't know, let's say 200 bits or something. So this is like 200. You're going to divide 200 by log of 200. It's going to be something. And then you're going to take the cube root of that. So you can imagine that d is not going to be monstrous. It's going to be a fairly small d. And that's what they did. And this gave rise to the number field sieve. Okay. So in the next lecture, what I want to do is I'm going to give an extremely hand-wavy exposition of the NFS, because I mean the NFS has so many different components in it. And there are lots of points where you're just going to hope for miracles to happen. Okay. So I will try to hide as much of the details as I can, but just give you the main idea of why these number fields even show up here. It's a beautiful idea that apparently started off with Pollard, who's also the Pollard's row algorithm, which it started off as a method to factor very specific forms of integers. So so Pollard came up with an approach to factor n that looks like something like r power a plus s, where r and s are small. Okay, for very specific sort of numbers. I mean, okay, for things that look almost like a power of something. It's like a power of something that has just been shifted by a little bit. Okay, and that was what was done. But then subsequently, people, I mean, like several people, Lenstra, Masse, a lot of people got involved and finally could show that no, you can actually make this work for all n. The number of miracles you want, that you need for this to happen, will become larger. But at the end of it, you can still make it work for all n. And again, the conjectured running time is L1/3 and not L1/2. And till date, this happens to be the best heuristic that we have for factorizing integers. Okay, so so this is I mean, we'll stop here, and the next class we'll look at the number field sieve and see what a high-level description of a number field sieve. I'll try to mostly tell you via examples, because I guess at this point you might also be wondering what are number fields. Okay, but I will describe all of them, and I'll give you, like, if everything goes according to plan, if the nature is going to conspire to somehow make you factor a number, I will tell you how the algorithm works. And obviously there are going to be a lot of other details which we won't be able to get into, but hopefully that is the main ideas. Okay, cool. So let me stop here and we will meet on Thursday. Okay, I'll probably adjust the video because of this, whatever, the gap in the middle that happened. I'll modify the video.